All right, want to welcome everybody back for the final contributed session of the 2021 workshop in geometric topology. Want to thank all of you for taking part and for hanging in here till the end. Thanks to the speakers in this session for being patient and waiting till this final session. So first speaker of the session is Ethan Farber from Boston College. And he's going to tell us about constructing pseudo-Anosovs from expanding interval maps. All yours, Ethan.
Great. Thank you, Craig. And thanks to the organizers for giving me this opportunity to speak. I'm very happy to be here. Like Craig said, I will be talking about how to construct pseudo-Anosovs from expanding interval maps. In particular, I have these two goals for the talk today, and I hope to get to both of them. The first is I want to give a parameterization of a special class of interval maps, which can be realized as the train track map for a pseudo-Anosov. I'll say a little bit more about that during the talk. But the meat of the talk is really going to be in goal 2, which is exploring some of the implications of this parameterization. So a theme will be that not only do we have some sort of abstract parameterization, but there is some substance to this. It's actually telling us something about these systems. Okay, so let's jump into it. There are two main characters in this story. The first are a special kind of interval map. So I will call a Zig Zag map a piecewise linear interval map F that satisfies these three properties. The first is that the derivative of F has constant magnitude, some number lambda that is greater than 1. The second is that the image of 0 is somewhere in the boundary of I, so either equal to 0 or 1. And the third requirement that I make is that the critical points of F are precisely I times lambda inverse, where this is the same lambda as the slope. And the picture to keep in mind is that these zigzag maps are starting at the boundary of the interval and then making full laps across the entire interval as long as they can until they run out of room. Okay. So this is a very special class of maps, allows me a good measure of control over them, which is useful in analysis. In this particular example, we have the zigzag map for slope 3 plus square root of 5 over 2. And I've marked out here the orbit of the point x equals 1 under this map. It's periodic of length 3. Okay. The second player in our story is something that might be familiar to you, a pseudo-Anosov, which I will usually write as a PA for short. This is a homeomorphism of a compact surface S that comes with some extra data. Okay. The first piece of that data is some real number, which I'm also going to write as lambda greater than 1. This is called the dilatation of the pseudo-Anosov. The second piece of data is a pair of singular measured foliations, which I'm writing as FU and FS. These foliations are transverse to each other. And the first FU is scaled by lambda under the homeomorphism. And the second FS is scaled by lambda inverse. Okay, so imagine locally we have charts on our surface where we have like horizontal and vertical lines, and the map is stretching the horizontal lines by a factor and shrinking the vertical lines by the inverse of that factor. Okay, here's a picture of a pseudo-Anosov. This is on a sphere with 4 punctures, and we can see what the pseudo-Anosov is doing to the sphere by looking at its action on each of these 4 rectangles making up the sphere. It's taking each one, shrinking it by the inverse of this number, and stretching it horizontally by that number, and then placing it back down in the surface somewhere. Okay. So I've told you what a zigzag map is, and I've told you what a pseudo-Anosov is. The rest of this talk will be about taking a zigzag map and making a pseudo-Anosov out of it, or at least looking at the zigzag maps for which we can do that. Okay. There's a process for doing this that was first defined by André de Carvalho about 20 years ago. He called this thickening an interval map. And it's a relatively technical and delicate process. And I won't really get into the details here because we don't have the time. But imagine that when what you're trying to do is you have an interval map. So you have some abstract interval and an endomorphism that maps it to itself. And you want to embed this interval into the surface, into some surface as a train track, so that the interval map becomes a train track map on that surface. Okay. There are some technical conditions here to make sure that everything works out. In general, you're just going to get a sphere homeomorphism, but in special cases, you actually do get a pseudo-Anosov. So if a bunch of combinatorics actually work out correctly, then you do in fact get these particularly nice sphere homeomorphisms. Okay. If the process does work, so if you do get a pseudo-Anosov out at the very end, then we'll say that the zigzag map you started with is of pseudo-Anosov type. Okay. These two pictures that I showed you earlier in the talk, they are sort of the before and after for an example of this procedure. On the left is a zigzag map, and on the right, this is actually the pseudo-Anosov that one obtains by thickening this map. And you might convince yourself that this is like morally what we get, because here's an embedded arc in the surface. Imagine that as an interval. And then under the transformation, this interval is stretched to the right and then back to the left and to the right again. Okay, and that's mimicking the behavior of this interval map. So if I can draw underneath, maybe here's abstractly the interval, and then here's the interval after it's been transformed. Okay. I know this is a little bit hand wavy. I'm ignoring a lot of, or I'm not telling you a lot of details. That's because this process is relatively complicated and I want to get to some sort of implications of our results. Okay. The central question before us is which zigzag maps, for which zigzag maps does this process output a pseudo-Anosov? So before we can state our first result, we need a few more quick pieces of information. The modality of a zigzag map, or just of an interval map in general, is the number of critical points. For a zigzag map, that number is always equal to the floor of the slope. I'll usually write that modality as M. Okay, and then I will define PA of M as the set of M modal zigzag maps of pseudo-Anosov type. So I look at all the maps, all the zigzags that can be turned into pseudo-Anosovs. I consider only the ones that have M critical points. That's the set PA of M. Okay. Here's a deep fact which requires analysis on its own to prove. There is a map, which I denote capital Phi, from the set PA of M into the rational numbers in the open unit interval. And this map Phi is determined by the dynamics of F. All right. Something to keep in mind is that this Phi is recording some sort of rotation that the map is inducing, that the map F is exhibiting. And in fact, if F is of pseudo-Anosov type, then phi of F is the rotation number of the corresponding pseudo-Anosov at infinity. Okay, but it's important to note that you can compute phi of F entirely on the interval side. You don't need to know anything about the actual pseudo-Anosov that it spits out. So our first result is that this map phi is actually a bijection for any fixed modality. In other words, we can parameterize the M-modal zigzags of pseudo-Anosov type by simply choosing a rational number in the open unit interval. And that's what we will be exploring in the rest of this talk. If we have rationals that are related in some way, then perhaps the dynamics of the corresponding interval maps are related in some way. Okay. Our example from before is a bimodal zigzag map of pseudo-Anosov type. So it's in PA of 2, and its rotation number is 1/2. So right in the middle. I want to emphasize that phi is not merely an abstract bijection. We're not merely stating that the set of zigzags of pseudo-Anosov type is countable. This is really packaging some dynamical data of the interval map. And the remainder of the talk is about sort of unpacking phi to understand what it's telling us. Okay. So as a first foray, let's graph this rotation number against the slope of the interval map. And I should say that the slope of this interval map, this is equal to the dilatation of the pseudo-Anosov that you get out. Okay. So if we graph the rotation number against the dilatation, we see some pretty interesting behavior. First of all, this graph appears to be monotone increasing. And second of all, there are large gaps present at all levels of zoom. So no matter how far I zoom into any of these rational numbers, if I go far enough, I will see that they are sitting sort of halfway between rational numbers that are limiting on either side. And so there appears to be no way to sort of extend this map to like a continuous map on any subinterval of the unit interval. Okay. So our two observations are that it appears to be monotonically increasing, and there appear to be these big gaps in the entropy or in the dilatation. So how can we understand these phenomena? Is there some explanation? And the answer is yes. The key tool comes from viewing the rational numbers as elements of the fairy tree. So the fairy tree, you might have seen this before. This is a way of this is a tree, but you can imagine it as a way to inductively construct the rational numbers in the open unit interval. Okay. The idea is that you start with the root 1/2 of the tree, and then you inductively build on either side of a vertex the mediant between that vertex and the one closest to it. So the mediant of 0 and 1/2 is 1/3. The mediant of 1/2 and 1 is 2/3. That gives you the second level of your fairy tree. And then to compute the third level, you'd look at this adjacent pair, compute the mediant, this adjacent pair, this adjacent pair, and this adjacent pair. And one thing I want to point out is that it's possible for two rational numbers to be close in the real line. For example, 4/9 and 5/9 are relatively close in the real line, but they are far away in the fairy tree. Okay? The fairy tree is giving some way of assigning an address or a coding to rational numbers. And even if you're close in the real line, your corresponding addresses might not look similar. And that appears to be borne out in the entropies, in the dilatations for these rational numbers. Okay, that's a little bit hand wavy. I can say something more precise. Given a zigzag of pseudo-Anosov type, there's a way of assigning to it a polynomial invariant called the Needing polynomial. This is an integral polynomial. It actually vanishes on the growth rate of your zigzag. And we can compute it explicitly. This is another fact that requires some work. So basically, if your zigzag has rotation number q, then that rotation number determines your needing polynomial. It determines the coefficients of it. So all you need to know is the rotation number of your zigzag, and that determines the needing polynomial's coefficients. Okay, let's record this sequence of coefficients as a vector, C of q. Then our second result is that if you're at a vertex of the fairy tree, and this vertex is the median of its two ancestors, A1 and A2, then you can compute the coefficient vector of q just by concatenating the coefficient vectors of its ancestors, A1 and A2. Okay. So in other words, as you walk through the fairy tree and look at the needing polynomials for each vertex, those polynomials are growing in a very predictable way. You're sort of like sticking more and more terms on for the higher powers based on what's come before. Okay. A little bit of needing theory then spits out this corollary, which is the monotonicity results that we observed sort of pictorially. So if you have two zigzags of pseudo-Anosov type, then the growth rate of one is less than the growth rate of the other, if and only if the rotation number of the first is less than the rotation number of the second. Okay. So already the fairy tree is bearing fruit for us. There's one other thing I'd like to quickly tell us about. Another use of the fairy tree. We've looked at the growth rates. We've looked at these real numbers, lambda. We can also, instead of looking at just those, look at, in fact, all of their Galois conjugates. These are algebraic integers. So you can think about not just them, but all of their Galois conjugates, and ask, is there any sort of interesting behavior occurring if we plot these in the complex plane? And the answer is yes. So here, pictured here, is the set of Galois conjugates of stretch factors of bimodal zigzag maps of pseudo-Anosov type. Here in the interval from 2 to 3 are the growth rates that we saw pictured earlier. And here are all of their Galois conjugates. So a few pretty fascinating things are apparent pretty immediately. The first is that these conjugates are highly concentrated around the unit circle, very highly concentrated. In fact, they appear to be dense on the circle. They also have what appear to be like pairs of parentheses that are showing up, spreading off of the circle. So can we understand where these parentheses are coming from? The answer is again, yes, and we can use the fairy tree to tell us why. Okay, so one final definition. We say a sequence Qn is fairy convergent if each element looks like this. This is basically just saying that the path that you're marking out in the fairy tree is a very simple one. Okay, so our last result is that if you have a fairy convergent sequence, look at all the zigzags of pseudo-Anosov type that give you those rotation numbers. Then the roots of their needing polynomials, the ones inside the unit disk, form convergent sequences. So they aren't just scattering around the open disk like noise. They actually are tending to well-defined limits in the unit disk. And that's describing this parenthesis behavior. These points here are actually Galois conjugates of some nice sequence of Zig Zag maps that are converging to some limit. Okay. And the proof sketch of this is very quick. Theorem 2 tells us that the coefficients of these leading polynomials we're sort of concatenating, we're building more and more terms just at the end on the higher powers. So term-wise, these leading polynomials are converging to some power series with integral coefficients. And the small roots, the roots with small modulus of a power series, are determined by the early terms, the low power terms. So that's a quick sketch of that proof. And finally, here are some images to sort of demonstrate what's happening here. So here's one sequence of rotation numbers. In here, I've pictured the unit disk, and you can see that we have some like convergent sequences of Galaconjugates in here. And the corresponding power series has roots at these 4 points corresponding to these 4 convergences here. Okay. And there's similar behavior in this sequence as well. Except this time the power series has 5 roots in the open unit disk. And let me stop there.
Okay, do we have any questions for Ethan? Thomas, you've got your hand up. Go ahead if you've got a question.
No, I was just applauding actually.
Oh, that's an applaud. Okay. Any questions? Okay, if not, let's thank Ethan for a very nice talk. All right, our next